not miss any of it. But if you do come in late and you want to catch up, we will put the video up online later on, so you can just go and catch up with the presentation. If you want to put your camera on as well, so people can see you, that's always cool. There you go. We have Jose there with the camera. What's going on there, Jose? It looks like you're in sort of coming out of a room. There you go. Yeah, found the way out. Cool. Right, guys, 3 minutes past. We're gonna have a start. So today we're gonna have this presentation as we scheduled there, using the unsupervised learning techniques we've been working on. I have two super guys here delivering this for you today. So we have Joseph Guy on there on the top, and John. So Joseph has been with the business for a long time. We go way back. You know, he's the digital project manager for ANSA in the digital side. So he basically knows everything there is to know about Clarity. Joseph has got a huge amount of experience. He's been on the oil and gas industry for over 15 years. And we'll be sort of delivering the sort of start of the presentation. We'll follow up with John. John is our machine learning engineer. So John is the sort of the brains behind all the clever stuff that that Clarity can do. So we started working with John when he was still doing his PhD at Aberdeen University, and we managed to sort of keep him on board, get him, you know, to continue that project, and he's been working with us ever since. So it's been a pleasure to work with the guys, and I'm gonna sort of hand over there to Joseph to start and get the slides on, and we can have a go. And if you have any questions, you know, just put it on the chat. I will keep them and we'll put them up at the end. And for the duration of the presentation, I will keep you guys muted. But when we get to the end there, when we're running through the Q&A, obviously we'll unmute anybody who wants to speak. So there you go, Joe, it's off to you.
Excellent. Thanks very much, Marilio, and hello to everybody. So if you joined us for our last webinar, where we gave an overview of how Clarity assists the user to process multi-finger caliper data, you saw how we went from importing the data to reporting on it. So you might be glad to hear that I'm only the warm-up act today. If you did come here just for me, I'm flattered, obviously, and I can link to a recording of that first webinar. So just for today, though, I'm going to give an introduction to the challenge of more accurately centralizing MFC data using unsupervised learning before John goes into a deep dive into the topic. So just very quickly again about ANSA Data Analytics. Who are we and what can we do? We're specialized in the processing and interpretation of cased hull logging data. So everything from pulse neutron surveys, looking at the reservoir information, through to what our topic today, which is multi-finger caliper data and the tubing itself. Just so you know where we've come from, just very quickly, we were there when multi-finger caliper data processing first got digital in the mid-90s, and more recently in the last few years when ANSA became a separate standalone company. That's when we started to develop ANSA. That's when we started to develop Clarity. In the last year, we've had Clarity in the hands of operators and service companies, and we're here today to talk a bit more in detail about the process. So I'm going to apologize to most people in the room. I think we all know why we're running multi-finger calipers, but just in case, what is it we're looking at really? So we're looking at the tubing and casing in the operating company's wells. Obviously, we're looking to assess deformation, deposition, metal loss features. What's a multi-finger caliper? Again, just very quickly, it's an old, trusted, reliable tool for the inspection of tubing and casing. It measures in the internal radius to assess what I just mentioned there, the corrosion, the damage, and the deposition, and the deformation. It's a easy to understand measurement. It's a tool that's been around for a long time. It's often run in conjunction with other services, so thickness services perhaps. It's always there. So why are we starting with multi-finger calipers? That's exactly why. It's there. It's trusted. But what's missing is a fresh take on the topic. So we're looking at how to utilize modern processing techniques on the software side, how to reduce human biases from having different people do the same job, and how to speed up the process. So just to give you an overall picture, if you were to tackle a job manually, you might be familiar with some of these steps. We talked about it in our last webinar, and we're going to be concentrating on just one of these steps just now. So we'll have a good deep dive into the topic of centralization, and John will be describing how unsupervised learning especially can make this task more accurate. Again, a little bit of an apology for people who know what we're on about here, but it's really important that we understand fully the start of the story. So this is just a simple diagram of a multi-finger caliper tool. It'll be supported as it's lowered and pulled up the well. It'll be supported by mechanical centralizers. So the purpose of these centralizers is to mitigate what is called tool eccentricity. So through unavoidable effects of gravity and the weight of the tool string, the multi-finger caliper will be sitting towards one side of the pipe that you're trying to inspect. So that distance between the ideal pipe center and the actual tool center is referred to as tool eccentricity. So why is this a problem? So in our ideal situation, this is very simply put, we have our pipe in the middle, or have a tool in the middle of the pipe taking a measurement of, in this case, 2.5 inches. So nominal pipe in this magical scenario, this gives you a nominal IR of 2 inches. So this 1/2 inch you would suspect to be a penetration into the wall thickness. So a 50% penetration in this scenario. That's what we're faced with as we log. So our tool is sitting closer to one side and further away from the other side. So in the same scenario with our 50% penetration, our measurement is actually only 2.25 inches. So that would be reported as a 25% penetration. This is a well understood problem, and this is what we're solving for you today with Clarity's prism centralization. Just to introduce a term, what we're going to use as we go on. So the features that we're trying to assess, so in the real world, we know them as deposition features or penetrative metal loss features. We're going to refer to these as outliers. And these are both the features that we're trying to describe, and also the thing that makes centralization of the data a little bit more difficult. So why is that? Let's take a look at what it looks like when we run centralization on the same data set here. This is the raw data. This is the processed version. So we'll zoom in a little bit on the one on the left. So just very visually speaking, in the red there, you've got radius values that represent the feature. And then we've got some blue shading there and some yellow and red shading opposite the feature. So the experienced eye knows that this is a visual indication of poor centralization. So whatever parameters have been applied as you press that button are not adequate to actually report the penetration value as accurately as you could. We'll just have a closer look again at both of them side by side. So the one on the bottom there has been processed better. So it all comes down to these outliers, and we'll explain those as we go on. We need to know which parameters, in the traditional world, we need to know which parameters to assign to these to this operation. The version on the bottom there will have a more accurate percent penetration. So how did I do this, and how have I done this in the past with old software? How do I cope with these outliers? So I can go through this. This is just 2 feet of data on the screen. I can go through this and I can create some zones manually. I can just look at that top section there and decide on what we call the outlier count, and we'll come back to the outlier count. We'll also be describing the geometric function as well later on, and the method of how I remove these outliers from the calculation. So I've got to do this for each of these zones, and I can get a good result by applying these parameters to this short section of data. So it only took me maybe 3 minutes to do that for 2 feet of data. So we all know that we don't log 2 feet of data. We log something like, here's 6,600 feet of data on the screen here, of raw data. So how am I going to centralize this? So if I was to try the same task, this table that on the right-hand side, it's not even big enough. I couldn't, you'd watch it scrolling past for the next 5 minutes. I can't adequately centralize absolutely everywhere. it's impossible for a human to do. You'd spend 1,000 years doing it and you still wouldn't get there. And that's really where centralization in clarity comes into it. So we've developed a method where you can better centralize the data at every single data point without having to enter any parameters yourself. And that's where AI and machine learning really shines. It's enabling more people to do the task of experts. And this is where I'll hand over to John, who's going to describe exactly how this magic is conjured from clarity.
Okay, so thanks, Joe. So hello, everyone. Now that we have a better understanding of what MFC data actually is and why we want to centralize the data, so over the rest of the duration of the talk, I'm going to be talking about how centralization is done and how we could leverage unsupervised learning for automating some of these tasks. So when we talk about centralization, really what we're trying to do is to fit all of these data points using either a circle or an ellipse, through which the new radii values is going to be calculated from the center of the fit. So using the red crosses there on both of the figures. And obviously there's pros and cons when you would want to use circle or ellipse. Circle is much suited for data set which does not have any sort of penetration features or depositional features. But ellipse is generally a better way to do that because it could account for, slight deformation or ovalization that might occur in the well. But whichever method that you choose, be it a circle or an ellipse, they're both quite susceptible to the presence of outliers. So in the slide here, you have multiple images of different scenarios having different sets of outliers. So moving from left to right, on the leftmost image, you have the perfect set of outliers. And if you are to perform an ellipse fitting, what you get is something rather similar to a circle because there's no other deformation on the other side of the well. But on the second image, you could see how just missing a single outlier could do towards your regression of an ellipse. And obviously, as you decrease the outlier set, the regression quality becomes poorer and poorer in such a way that the ellipse regression doesn't reflect the true geometry of the pipe. And you'll see later on how that could result towards your penetration calculation. So, and obviously that was only on a single depth slice. But when you are presented with raw data, like the one you see on the right, what a user typically have to do is something along the lines of the flowchart on the left. So the first thing that they'd have to do is to separate data into zones, typically by visually clustering it. So for example, the first 2,500 foot, you could see that there's a lot of deposition features over there. And for that reason, they will want to, for example, remove the minimum 10 arms in that region. But in the subsequent zone, you see less of that deposition, which is why they would reduce the number from 10 to 7. But following up on this flowchart, they could iterate the selection of zones, the selection of parameters until it is deemed satisfactory by the user. And this takes quite a bit of time. And also, just to give you a bit of visual understanding of what this minimum, maximum 5 actually is, this manual selection of parameters. So for each of the section, the user will have to select what type of fitting they're going to use, so either circle or ellipse, the type of removal, so maximum, minimum, or absolute, and the number of arms to remove. And what this maximum, minimum, and absolute value actually means is that, so suppose that you have a profile that you see on the left there. Hopefully you can see there's a few depositional features over there. What we can do at the start is to perform an ellipse fitting using all of the arms, which is shown by the black dash line over there. And from that, you can calculate the residual plot, which is shown on the right. And that is simply just by calculating the distance between each of the point to the surface of the ellipse. So for example, if we are to use the parameter of removing the minimum 3 arms, you'd be removing that arm, those 3 arms over there. But the point here is that the user will have to decide what sort of parameters that they're going to choose. And this is exactly what we're trying to automate here in Clarity. So during the development for a solution of automatic centralization, there are really 3 aspects that we're really thinking about. The first is explainability. And what we mean by that is we want a method that's able to convert the raw data into the centralized version in such a way that that would provide a profile at each step on which arms is it that they're removing. And that brings me to the second point on computational complexity, which means that we want an automated method that doesn't take 3 or 4 hours, because that would defeat the whole purpose of trying to speed things up through automation. But at the same time, we want to have high enough accuracy. So we need to strike the right balance between computational complexity and accuracy here. So during the development stage, we found that it's sometimes can be quite difficult to correct for eccentricity, because in order to do that, we need to select the right outlier set. But to select the outlier set, it can be quite difficult as well, because it is masked by the eccentricity. So this is a bit of a chicken and egg problem, really. And the way that we try to tackle this is through a 2-step solutions. So the first step here being the estimation of the eccentricity. So we call this percentilization. And this is what you see on the figure on the right there. So hopefully you can see that there's a lot of eccentricity happening in the raw data, and that is removed effectively by our percentilization technique. But just as a pretext to that, I have a slide here showing you what density-based clustering is, so DBSCAN. So this is an unsupervised method, which means that it doesn't require any labels for it to work. And it's also a clustering method. And the way that it's clustering is simply based on the density of data points. So it looks at how close is each data point to the surroundings. And it's a bit different from some of the most common clustering methods like k-means, or if you're familiar with self-organizing map, which requires you to predefine how many clusters there are going to be during clustering. And DBSCAN also doesn't make any assumption on what's the shape of the cluster supposed to be. So how can we use this? So the next slide here, we have so we have a profile of a 40-arm tool, as you can see on the left. And because the number of fingers are even, for each arm, we can actually draw the line to the opposite arm directly 180 degrees from it. And if we do that for each of the arm, we get the image on the left. We can call it directional diameter here. But if we really zoom in into the black box on the left, you can see that these magenta points are actually the middle point of all of those directional diameter. And turns out, if we have a look at the center of those magenta points, actually they're pointing more towards the center of the pipe. So our heuristics here is based on trying to resolve this effect of eccentricity by iteratively moving the center of the tool towards the center of those magenta points. So if we are to have a look at it visually, so on the left, hopefully you can see that there's a 24-arm profile, which is slightly decentered. And if we are to do that iteration that I just mentioned before, you could see that by about iteration 5 or 6, it would have it converges into the middle, and by doing so, it effectively removing the effect of eccentricity. But obviously, the data here is very nice. It's clean, doesn't have any sort of penetration features or deposition. But would this also work if the data is corrupted by noise? So on the figure on the right, you can see there's a bit of deposition on the bottom left over there. And if we do this precentralization heuristics, you could see that it's trying to undo the effect of eccentricity, but you could see that not all of the circles are converging towards the end of the iteration. So we know that there's some effect of that this method is still affected by the presence of noise. And in the next slide, what happens if we increase the magnitude of these of the outliers? So if we play the video on the left there, you could see because of the presence of those outliers, those points tend to be more scattered, and our method, precentralization method, ends up having a similar result to just centralizing the data using all of the arms. So if you look at the figure on the left, the comparison, you could see how doing this precentralization gives you a centralization artifact, which is something that really we want to avoid here. So this is where a DB scan can be useful. So if we are to do the same thing here, but this time around we use DB scan at every iteration, we're only going to be using data points which are closer with each other. So effectively, they're ignoring all of the data sets that's scattered on because of the presence of the outlier. So consequently, when you apply this heuristics with DB scan, you could see that the precentralization is much, much better than without applying DB scan at all. So just to show you as well on how this would look like on real data, this slide here shows what precentralization would have an effect on data set which is heavily affected by deposits. And if we have a look at the profile at this red line on the left, you could see how the precentralization actually converts the blue line, which is the raw data, into the red one. And when doing so, we are exposing the outliers a bit much better. So how does this translate into penetration features? So, because that's the most important bit. So if we consider all the images on the top, so these are the raw data, and if you are to apply a standard outlier detection technique like median absolute deviation, you'd get the outlier shown by the yellow circles, which is actually the wrong part of the pipe that you want to remove during the ellipse fitting, right? So when you remove those parts, what tends to happen here in the middle top image here is the ellipse regression will try so much to fit into the noise, but in such a way that it's going to push out the clean part of the well. And consequently, when you calculate the maximum penetration, so on the top right image there, you can see the maximum penetration value there is 50.8%, which is really quite significant. But really, if you apply precentralization to the data, so you're considering the green line here on the bottom left, and applying median absolute deviation, you end up with a different profile. And consequently, when you remove these data points during regression, you end up with a different maximum penetration value on the bottom right there. So 21%. So 50% to 21%. That's really quite significant. And if you are to simply look at the face value, this could result to cost implications of your forward plans, whatever it may be. And also, obviously, this is just at a single depth profile. And so far I've just talked about pre-centralization, which doesn't necessarily show you how the noise is being or the outliers are being found, because really it's just trying to undo the effect of eccentricity. So on the next slide here, we have another technique to help us try to highlight some of these noise. So what you have here is the schematic of what an autoencoder is. So essentially, an autoencoder is an unsupervised learning method as well. So it doesn't require any sort of labels. And the objective of the autoencoder here is to reconstruct its own input. So in this example here, you have an image of a digit of 2 as an input, and it's going to pass through this model with a bottleneck. And on the other side, it's going to output this the reconstruction of that input. So you might think, so how is this useful? So this can be quite useful. For example, if you are to input all of the digit images, like for example 0 to 9, during the training phase, and for deployment, if during deployment the data set does not really have the same sort of distribution as the training input. So if you are to pass letter images instead of numbers, you'd get a bad reconstruction of the output because it hasn't seen that data before during training. And that is one way that we can use it for outlier detection. But there's also a variant of an autoencoder. So this is called denoising autoencoder, which has a very similar workflow. But this time around, instead of giving it the clean version of the image, we give a slightly distorted image. So by distorted, I mean you can add it a bit of noise. So in this case, you can add some random Gaussian noise as an input to this model. But the objective of the model now, instead of fully trying to reconstruct the input, we're trying to reconstruct the noisy version of the input. But then now the question becomes, how is this useful for MFC data? Because when you receive the MFC data, you don't get the noise and the pipe data separately. It comes as a summation of both the noise and the pipe. So this is where your synthetic data can be quite useful. Why synthetic data? Because you can easily model the shape of the pipe with randomized ovalities. You can model stuff like noise and also eccentricity. And it's quite trivial to do that. So in the images here, you have the example of synthetic data. So the synthetic data here is on the left. And the one in the middle is the synthetic data with added noise. So hopefully you can see like speckled pixels within the image. And the last one is the synthetic data with noise and eccentricity. So the banding is what the effect of eccentricity looks like. So the idea is quite simple. Is to perform denoising autoencoder into this synthetic data. So you feed in the noisy synthetic and train the autoencoder to predict what noise-free synthetic would look like. Because we create the synthetic data and noise separately, so we have the ability to do that. So how this would look like on synthetic data itself is something like this, where you have the synthetic data with noise on the left. And this on the second panel is, you can call it the ground truth. So that's the synthetic data without any noise, so the noise-free version of it. On the third panel, you can see the prediction of the synthetic data. So this is the output that you get from the autoencoder. And what we can do after we pass the data from the autoencoder is to subtract the original input from the output. And that way you get the difference between the input and the output on the right. So this highlights, the potential noise at every depth and fingers. And also because this is a synthetic data, we could plot the performance plot, and we only have like five points here, each of which has a different workflow. And the way that I use and the way I calculate the true positive rate here is using median absolute deviation, and it's because it's quite a convenient metric to gauge how well each of this workflow is, because it doesn't require any sort of parameters. So on the first point there, that's the true positive rate. If you are to simply use the raw data and pass it down to median absolute deviation, you get a true positive rate of detecting outliers just under 40%. The second data point here is to centralize using all of the arms. So it improves it slightly. Our precentralization heuristics gives a slight improvement as well, but we see most of the jump here when we apply precentralization heuristics with dbScan. So that pumps it up to 55%. And we get the most performance when we put all of these things together, when we perform precentralization with dbScan as well as pass it down to an autoencoder. So we can also calculate the confusion matrix of what this traditional workflow against our new autoencoder workflow. So as was mentioned before, our traditional workflow will require the user to select how many arms is it to remove. So the confusion matrix on the left shows you the result of choosing absolute 4 fingers. The one in the middle shows you the confusion matrix of choosing absolute 10 fingers. And you could see that true positive rate increases from 43.7 over there to 70.2% when you change the value from 4 to 10. It makes sense because you're removing more arms. But at the same time, if you look at the true negative rate, it goes down from 97 to 84. And this means that you're effectively removing more arms than you should. And this is where exactly why the user have to define the zones, because some zones might have different parameters that's better suited than the others. But in our autoencoder workflow, now just by a single click, now you can have a true positive rate of 82.2%. So that's quite significant for comparing to the traditional workflow with a very low false positive rate. But obviously, what I've just shown here is just the result on synthetic data. And on the next slide here, I have the deployment of autoencoder workflow on real data. So on the figure on the left, you have the raw data with lots of deposition and eccentricities. And on the second panel, you got the precentralization using dbScan. So hopefully you can see that there's the effect of eccentricities are massively reduced. On the third panel is the output from the autoencoder, where it's trying to estimate what the data would look like had it not been affected by the deposition. So subtracting the third from the second panel gives you the difference field, which you can pass into either median absolute deviation or some other a standard outlier detection method. So in the last slide here, I'm just going to show you what it looks like in clarity when performing automatic centralization. So you have the raw data on the left, the centralized data on the right, and in the middle you have the profile of which arms is it they're removing at every depth. So this is again the value that is created when performing this workflow is that you don't need to select how many arms is it to remove, do some spatial or visual clustering. And yeah, so it also doesn't mean that the work ends here, because as you see, there's still room for improvement. So in the future, we're looking into adding more types of input into the autoencoder. So stuff like the tool upside and deviation can be a good prior for resolving this problem. So with that, just to sum it all up, today we have a look at what is MFC data, why we want to perform centralization, how we did centralization using legacy methods, and also how unsupervised learning techniques can be used for automating some of these problems by breaking this problem into precentralization and anomaly detection. And with that, yeah, thank you for listening, and I'll pass it back down to Aurelio.